Hello, I am Paul Dean, a research associate at Lancaster University. Today, we'll be demonstrating our work on behalf of the AI4ME project, a partnership between Lancaster University, the University of Surrey and the BBC, with the goal of delivering personalised object-based media at a large scale. Our work focuses on autonomous compute migration and cache reusability, with compute meaning an operation that we perform, such as rendering, shading or compositing. Our first demonstration of autonomous compute migration explores deploying our individual objects, in this case time image or subtitles, to our remote location. In this instance, it is our remote servers hosted within Lancaster University's data centre, with the round trip time above displaying the time it takes for data to be sent from here, our current location in Manchester, to the servers in Lancaster University's data centre. To begin, we'll deploy our object-based media client. This is currently hosted locally and is separated to show the individual layers. In this instance, we have the presenter, we have the map, time image and subtitles. Each of these are represented on the larger dashboard as S for subtitles, T for time image, M for map, V for the presenter and G for the GUI. In a moment, they will become discoverable, and the machine learning agent that we have paired with the client will begin to discover remote locations and explore these resource containers, then making the decision if the reward is beneficial. In this instance, our reward is a more efficient rendering process. As we allow the client to identify resource containers available, they will begin discovering the locations. The code required for network communication will be dynamically injected into the client, and the client will then begin offloading compute to identify the resource container available and whether or not the rendering process is more efficient. And from this, we'll repeatedly search between the local and remote implementation, eventually deciding on a decision on where to place the offloaded compute, which will best help the rendering process. As you can see, even while the machine learning agent is repeatedly exploring the current environment that we have set, the client's experience remains unaffected as it switches between both local and remote computation with no change or degradation. To perform this operation for multiple clients, however, is expensive, which moves on to our next demonstration, cache reusability. In order to lower the cost while maintaining a quality experience for clients which do not have the computational resources to perform it locally, we look to lower the compute required by doing cache reusability. What we mean is that for each frame that we would individually render in these clients for map or time image, we separate them and deploy them, saving the result and sharing them between connecting clients with close temporal proximity. This can be seen when we begin our next demonstration and set 4 clients to be connected to the remote servers. As we begin our 4 clients, they will begin identifying the resource containers available as we allow time image and subtitle to be identifiable. Each of these clients will begin the process of identifying the resource container available, as seen previously, perform the compute migration, however this time deciding on the placement choice to be remote. This allows us to see the reuse between each connecting client as the results are shared via the cached frames. The reuse that we see will dynamically change over time as the individual frame stored has a higher lifespan within the time series that we see. In this instance, time image would persist for longer than a subtitle would for the given frame and have a higher reuse. This changes over time, but still reduces the cost for many connecting clients. Our future work looks to explore this problem at a much larger scale, with millions of connecting clients over geographically dispersed locations, and with a more complex rendering process. While our current work has looked at exploring the autonomous compute migration using an online learning agent, carefully balancing the exploration process where we must find all resources available, and then exploiting the found placement locations that we have to achieve a more efficient render, this creates a complex machine learning problem, as we must understand when we can stop exploring and start exploiting the placement decisions that we have made. This branches onto future work, where we have a more simpler render process now. In future, we look to have a digital presenter or dynamic lighting added. This creates a more difficult process, as we must then understand the complexities of each of the individual compute and how this may also change placement locations. Another aspect of our future work, where we explore the decisions that we must make and the placement locations we have found, and what metrics we use to decide that placement location is a good choice. What this means is that we can have geolocation, the latency among a client, the cost of spinning up a new container, or even the proximity in a timeline of a show for media content that we have, and whether or not they can be co-located on any of those properties. This creates a large number of properties that we can exploit for placement decisions and a more complex problem to explore in the decision-making process. Thank you for watching this demonstration, and we look forward to showing you our future work.